Hello everyone. Let me start with a simple question. Have you ever noticed how a chandelier hanging from the ceiling stays perfectly still? Or how a tightrope walker manages to stay balanced despite multiple forces acting on them? This state of balance is what we call equilibrium. In mechanics, equilibrium means that the net external force on a particle is zero. And according to Newton's first law, if the net force is zero, the particle either stays at rest or moves with uniform velocity. Today, let's explore how forces can balance each other to keep a particle in equilibrium. Let's first look at the simplest case, two forces. For a particle to be in equilibrium under two forces, the forces must be equal in size and opposite in direction. In that case, their vector sum is zero. Think of a book resting on a table. The downward force of gravity is exactly balanced by the upward normal force of the table. The equation is simple: force 1 equals negative of force 2. So, as long as these two forces cancel out, the book remains still. Now let's move to three concurrent forces, meaning three forces meeting at a single point. Here, the condition of equilibrium is that the vector sum of the three forces must be zero. In words, force 1 plus force 2 plus force 3 equals 0. Graphically, this means that if we represent the three forces as arrows taken head to tail, they should form a closed triangle. This is sometimes called the triangle law of forces. So if you can draw a closed triangle with the three force vectors, the particle is in equilibrium. What if more than three forces act on a particle? The rule still holds. For a particle in equilibrium under many forces, the sum of all the forces must be zero. In component form, we say the sum of all horizontal forces equals zero and the sum of all vertical forces equals zero. Graphically, when all the forces are represented as arrows one after another, they must form a closed polygon. This polygon rule is just an extension of the triangle law.
Let's express it step by step. If three forces act on a particle, let's call them F1, F2, and F3. Then the condition of equilibrium is F1 plus F2 plus F3 equals 0. In component form, the condition becomes the sum of the x components of the three forces equals 0, and the sum of the y components of the three forces also equals 0. In simple words, balance along the horizontal direction and balance along the vertical direction both must hold simultaneously. Now let's solve a problem. A 6 kilogram mass is suspended by a rope of length 2 meters from the ceiling. A horizontal force of 50 newtons is applied at the midpoint of the rope. What angle does the rope make with the vertical in equilibrium? Take g as 10 meters per second squared. Step 1. The downward weight of the mass is 6 multiplied by 10, which is 60 newtons. Step 2. The rope must supply enough tension to balance both the vertical weight and the horizontal pull. Step 3. In the horizontal direction, tension multiplied by sine theta equals 50. Step 4. In the vertical direction, tension multiplied by cosine theta equals 60. Step 5. If we divide the two equations, tangent theta equals 50 divided by 60, which is 5 by 6. So theta is approximately 39 degrees. That means the rope makes an angle of about 39 degrees with the vertical when in equilibrium.
Let's quickly recap. A particle is said to be in equilibrium when the net external force on it is zero. For two forces, they must be equal and opposite. For three forces, their vector sum must form a closed triangle. In the general case, the sum of all horizontal forces and the sum of all vertical forces must each equal 0. This principle explains why suspended lamps don't fall, why bridges remain steady, and why engineers carefully calculate forces to keep buildings and structures safe. So to sum up, equilibrium is the secret behind stability in the physical world. I hope this session gave you a clear picture of how equilibrium works. See you in the next class with another fascinating concept of physics.